okay, breaking various copyright laws. But I figure we have enough actual copies for you guys to like take it around. So like, you know, in a way, you have enough of the copies. We just don't have them physically with you, you know. So maybe I shouldn't say this while I'm recording, but oh well. All right, guess so you guys can get me in trouble if you don't like your grade on your test or something like that. There you go. Okay, double vengeance. So, graphing quadratics in standard form. All right. So first of all, let me just refresh our memories here. A quadratic function okay. This is any function that can be written in the form ax squared plus bx plus c, or I should say y equals ax squared plus bx plus c. With one little caveat, we have to further specify that a cannot be equal to 0. Okay? So that's the definition of a quadratic function. Why is it important that we specify that a cannot be equal to 0 here? What would happen if a was 0?
Because then x wouldn't matter. X matter.
Yeah, so our x squared term there, bless you, our x squared term has the a as its coefficient, right? If a was 0, it would be 0 times x squared. What would happen to the x squared term? Christian said it would go away, right? And then what kind of function will we have if that goes away? Is this still quadratic? No. What is it?
A non-quadratic.
Non-quadratic. That is very non-specific, but true.
Linear.
Linear. It'll be linear, right? Because there's your mx plus b, right? Or your slope-intercept form right there. Okay. So without that a existing, right, then you wouldn't have quadratic. So we need to specify that. Otherwise, you know, but there's the exception. What if a is 0? Well, that's not quadratic. Okay. So we already spent some time, like I said, graphing the quadratic function. So we'll talk about the parent function here, and we'll get more into transformations tomorrow. Okay, but there's going to be a little bit of transformations today, but mostly tomorrow because that's really the vertex form where we see a lot of the typical transformations. The parent function, though, is y equals x squared. Okay, again, I will re-sketch it here because it was in our warm-ups, but our warm-ups get turned in. I'm not going to go through all the domain and range stuff again with you, but bless you. Okay. I'm going to endeavor to try and make it a pretty decent, graph here, not just willy-nilly sketch, but you can graph it as accurately as you'd like. It's like a little Bob Ross going on right now, okay? Just happy little trees. Okay. Okay. And yeah, I'm going to redraw that table too, just because I'm going to maybe use that to help us out here. So again, anatomically, right, we have this point right here. That's called the vertex, okay? It's going to be, the lowest point or the highest point of our parabola, depending on how our parabola is, displayed, I guess, or how it's transformed, okay? We also, Michael mentioned how this is an even function, which means we have symmetry specifically over the y-axis. But our parabolas will always be symmetric, have a line of symmetry, okay? And that line of symmetry right? We call that the axis of symmetry. Okay. The axis of symmetry will always be x equals, and then for standard form, okay, there's a formula that I'm just going to give to you for our purposes here, okay? It's like the front half of the quadratic formula, negative b over 2a, right? So if you remember the quadratic formula, I'm sure you all have it down in your heads right now, right? But just in case you need a refresher, okay? The negative b plus or minus the square root b squared minus 4ac all over 2a. A little bit of a vision of the future. We will be using this in the future. All right, there's that vertex calculation, right? And then we add or subtract, the discriminant there, the square root of the discriminant, to get our zeros, right? But there's that, the vertex part. The axis of symmetry is right in the center of the parabola. Okay. So that's the axis of symmetry calculation, which we'll then use to help us find the vertex, because the axis of symmetry is always going to go through the vertex, right? That vertex is that kind of center of the parabola there, which means the x-coordinate for the vertex will always be what? Sure.
0.
Well, in this case, it's 0, but if it's like transformed or something like that, it might not be 0, right? But if we know our axis of symmetry is always of this form, x is equal to negative b over 2a, that means the x-coordinate for the vertex will also be negative b over 2a. Okay? Always will be negative b over 2a. And then once you know the x-coordinate for your vertex, what can we do to that x-coordinate to figure out what the matching y-coordinate is? All right, I'll leave that blank then. Okay. So let's practice sketching some of these graphs, and we'll come back to that while you guys think about it. Okay, and again, we're just going to sketch the graph. I know this is really rough because I didn't give you guys graph paper, but we'll just all suffer together. Okay. Okay, so let's just try one here. So number one, we'll do f of x equals negative 1/2 x squared plus 3. When it comes to standard form, there's a lot of different things we could potentially do here. In fact, our strategies will kind of grow when it comes to graphing. Our strategies will grow as we learn more here. But for right now, since we're starting on the very basics, I'll kind of help lead you through this somewhat here. Okay. The first thing I'm going to recommend we do is that we get the vertex. Okay, and again, x equals negative b over 2a, right? Okay. Then I'm going to recommend that we make a table. Put the vertex in the center of the table. Okay. And then I don't know, pick points before / after the vertex. Okay. And then plot points / graph. All right. That's what we're going to be doing here. Okay. We're going to find that vertex just like we kind of like prioritize the vertex and the absolute value, right? The first thing that we did whenever we were transforming the absolute value function is we identified where that vertex was. Once we had that vertex, then it was a matter of just figuring out the rest of the graph from there. Okay? So that vertex is like the key point, and that's going to be again a major theme in all the functions that we learn about in this class. There's going to be some kind of like single point that you're going to use to help you transform, and then from that single point, you'll then get the rest of the graph. You kind of fill it out. It won't always be called the vertex, I don't think, but a lot of times it will be like the vertex. Okay, so vertex. Okay, right. X equals. So what is our b in this function here? Three's there, yeah. -1/2 is there. There is no b. Exactly right. There's no x term here, right? If you go back up here to standard form, it's ax squared plus bx plus c. -1/2, that is our a value. 3 is our b or c. C, right? There is no b value. If there's no b value, what number do we use to represent no number? Well, x would be the variable. What number is there if there's no x? 1x would mean we have 1x. We have no x's. So it's 0. We have 0 x's. So our b value here would be -0 over 2 times, and what's our a value? -1/2, right? We identified that there. So just put the -1/2 in. Okay? Is this a problem that we're doing 0 divided by a number? Does that cause a problem with math? Is that a problem?
Yes.
It doesn't work.
Yes.
Is it only
But, pretty sure.
Yes, no, don't know?
I'm pretty sure.
if you divide something, if 0 is divided by anything, it equals 0.
So 0 divided by a number is 0. A number divided by 0 doesn't exist, undefined, right? Okay, so different things, right? But be careful there. And the beauty of this is if you try to see your calculator, you'll get 0. But if you don't have your calculator, right, you need to know that that's 0. Right? That is no problem. 0 divided by anything is going to be 0. Okay, 0, but a number divided by 0 is undefined, right? That's where we run into problems. And then there's also the weird situation where you have 0 divided by 0, and that's a completely different thing altogether. Okay, so we won't worry about that right now. Anyway, our x-coordinate for our vertex is 0. So right now I have my vertex has x-coordinate of 0, but I don't know the y-coordinate for my vertex. How can we figure out the y-coordinate is?
You square the x-coordinate.
Say what?
You square the x-coordinate.
Just square it? That's all I need to do? Close. That's part of it. We will be squaring it. What else? Your mind? Right. Remember, we're trying to graph this thing. The vertex, is it on our graph? Is the vertex going to be on our graph? It will be on our graph, right? It's going to be part of the function. So 0 must work in my function. So I can put 0 in, plug it in, just fine, f of 0. And so that was the answer to up here. It's just, you just do f of then -b over 2a. Okay? You're going to plug in the x-coordinate to get the matching y-coordinate. So we're going to plug in the x-coordinate here, and what do we get when we plug in 0 for that function? 0 squared is 0 times 0, plus 3, so it's 3. Okay? Yeah, it's 3. Okay. Okay, so we get 3. What? 0, 3 is our vertex. Okay? So, now we have that vertex, let's make a table. Okay, sorry if this is, childish to you, Mr. Wade. Is this, we're going to make tables? Yes, yes. That's what you need to do. And to start out, yes. Okay? I'm going to pick some x values before 0, so like -1, -2. I'm going to pick some x values after 0, like 1 and 2. Okay? And how do I get these matching y values? Where are these? How am I going to fill in these blanks? Yeah, plug in the x values. Exactly right. Plug in the x values. Okay. So I'm going to do that mentally here, right? So -2 in for the x, right? -2 squared is 4. 4 times -1/2 is -2 plus 3. Ooh, -2 plus 3, 1. Okay, and let's do -1. -1 squared, 1. 1 times -1/2, -1/2. Okay, -1/2 plus 3. Oh, Mr. Wood, fractions, really? Yes, really. Okay, so -1/2 plus 3 is 2.5 or 5 halves, whichever you prefer there. Okay, plug in 1. 1 squared is 1, times -1/2 is -1/2, plus 3 is, again, 2.5 or 5 halves. And then plug in 2, and what is 2 when you plug it into our function there? 1. Okay. Questions on any of that? Do you see some symmetry here? Okay, so we had our vertex there in the center. I went 1 before and then 1 more before, right? -1, -2, and then I went 1 after and 1 more after, okay, in the x coordinates, right? And so that results in creating symmetry here, all right? You should get these results, and if you want to take advantage of that, right? So in other words, if you just want to figure out what 1's y value and 2's y value are, you can then, use the symmetry for the other 2 points there. You don't have to, do the calculation yet, but if you want to, just check yourself, that's fine too. But feel free to use the symmetry that Michael pointed out to us here when we said this was an even function. Now, this one also happens to be an even function too. They won't all be even, but they will all have symmetry. Okay, they won't all be even, but they will have symmetry. And then we'll just plot the points, right? So. By the way, your x and y axis don't have to always cross like in the center of each other, right? For example, here, I know my function, my quadratic, right? There's no negative y values. Okay, they're just going to keep going up and up and up and up. Or maybe they will have negative y values, but I don't have any here that I have to graph, I should say. So you don't have to do that. Okay, you can kind of adjust things. In fact, I would encourage you to as you graph more and more, I would challenge you to try and not always draw your x and y axis the same way every time, right? Try and think about where your graph will be so you can adjust your axes to make it, fit better inside the function, or fit better, the function fit better in your axes and stuff. Okay, so here I made some adjustments, right? So anyway, let me plot these here. So 1, 2, 3. So I just plot the points. 0, 3. I'll do this with a different color here. So 0, 3. Okay. And then I'll do these ones. -2, 1, 2, 1, and then -1, 2.5. 1, 2. Maybe something like that. And voila, we have our graph. Okay. Does anyone recognize any transformations of this from our original parent function of x squared? What kind of transformations do you see here? Okay, reflection. And you can see here our a value, yes, that is the same a that we were talking about back with absolute value, that a parameter. A is negative. Okay, what else? Sorry, what else? So we flipped it, what else?
3.
Okay, it shifted up 3. And let's take a look here. There's that plus 3 on the outside, right? Shifted it up 3. Okay. What about that 1/2? What do we expect that 1/2 to do? What does a 1/2 in front of our function do with absolute values? A dilation, yes, exactly right. A shrink or a stretch? Shrink, right, because it's times 1/2. And so this like smushed down a little bit. Okay, so it flipped, shifted up 3, and smushed down. Okay, and again, don't fret too much about that. We'll focus more on the transformations and things tomorrow. But I mean, there it is, right there. Okay, you can see it. Okay. All right, very good. Let me have you guys try one then. See how we do. Okay, so again, trying to pick something halfway decent here. Let's see. All right, I'm just gonna make okay. Let's see if I'll put the directions up there. So is this graphic standard form? Yes. So you're going to need to identify your A, your B, and your C, right? Get the vertex, make a table, pick some points for the table, plot the points. Okay, and then connect it up. Right? So go ahead. All right, go ahead.
Okay, I will do the same thing.
Feel free to use whole numbers too when you go to fill in your table. Okay, I know the vertex, okay, doesn't end up being a whole number, you know, that's fraction stuff, but feel free to use whole numbers when you're filling in the rest of your functions, stuff like that. That's fine.
point. Once you have the points, you have to do that.
No, that's exactly right.
Yeah.
Let's try. Okay, so let's turn off these plots here because that's probably going to mess up your graph too. So, what's the vertex? Okay, I'm going to go to get the vertex. X equals negative b over 2a. Right. So what's your b in this quadratic function here? So what's the number? What's this number right here in front? 1. And so what's your a value? A 1 as well. Yep. So you're going to have to plug in 1 for b, 1 for a. Get your x coordinate. Once you have the x coordinate, plug that in to get the y coordinate. Okay. What's up, sir? What do you think? Yeah. So there's an error somewhere, right? And that's good. We recognize that. We want to go right with that. So let's see. So, which one of these points is your vertex? Okay, and how did you know that? Okay, so x was 0 for this one for our vertex because when we calculated the vertex, it was negative b over 2a, right? And our b in this case was 0. What's our b value here? Negative 2 is c, right? It goes a, b, c. Yeah, what number is in front there? 1. So it'll be negative 1 divided by 2 times a. What's our a according to this? 1 as well. Yep, so 2. So that's your thing. So then your vertex calculation here is going to be negative 1 over 2 times 1, right? Negative b over 2a, which is negative 1/2. So your middle point here actually is to be negative 3. Nope, you don't have to actually calculate by plugging negative 1/2 in to get that nice y value. Okay? And you go, so negative 1, negative 2, that's fine. Let's go to 0 next, and then 1 right here. Okay? Do some points that way. Yep. Yes, sir. Oh no, what happened? Let's see. You're very close here. I feel like that's good. That's good. That's good. Oh, I see. These, okay, one of these is off. So negative 1, so negative 1 squared is 1, plus 1, plus 1 be 0, minus 2, so that should be negative 2. And you can also kind of, again, take advantage of that symmetry a little bit there too, right? This is 1/2 more, this is 1/2 less, so they are both equidistant in that center. So we should both have the same y value, just like these are both, 1 and negative 2 are both equidistant to that vertex, so again, they share the same y value as well. Okay, and so now you should get that. Anyone else need some help? Yeah. Let's see. So yeah, that's, it should be, is that a negative 2.25? Should be 2.25. Yeah. And then everything else, you know, as long as you plug points in. Are you? Really? Well, I guess so, Claire. I guess so. You didn't. You're just trying to. So what are you trying to do exactly? Are you trying to figure out what this is equal? Oh, I see what you're saying. You want to type that into your home screen, right? Because that's not going to your home screen get that value. You want a number, so you go to second mode. And now type that in, okay? Okay. Give people like 1 more minute here. 1 more minute. That's very kind. Who's your friend?
MK.
MK. That's nice. And we all wish we had a friend that would bring us a breakfast sandwich. That's one to starve. Go ahead, eat it. Eat it, Claire. We'll just watch you. I'm sure it's going to smell up the whole room, too. It's going to smell very good.
Don't you have to bring one for everyone?
Maybe Claire's planning on cutting it up into, teeny bites for us all to have a little piece. Maybe. You want a knife, Claire? All right. Well, here's the answer. Okay, here's what we should have got. Okay, your vertex was at -1/2 x coordinates, which means your maximum y coordinate is -9/4, or as a decimal, -2.25. Okay. Then for the earlier points, right, I went -1/2 more negative. Okay, so I went back 1 more half to get to -1. And then -2. And then from here I went up a half to 0, and then up a full to 1 there. Up full, 1 quarter to 1. Okay? And that gave me some extra points there to plug in, and then find the imaginary y values and get our answer there. So yes, question?
Can I go to the bathroom?
Sure. Okay. Feeling okay on this stuff? Yeah? Okay. Any questions on this? Any questions on this? Okay. So yes, that's the idea. All right. So that one was admittedly there won't be all. Yeah, I'll try to avoid the fraction ones for these just because of the nature of what we're doing and stuff like that. Okay, but that's the idea there. Okay. So when it comes to talking about these parabolas, right, we kind of have 2 basic shapes of the parabola we're going to see. Okay, we're going to have, this shape, right? Might call it like a U kind of shape. And then this shape, which you might call like a bell maybe, or I don't know, upside down U, okay? Different ways people describe this. Like this one opens upwards. This one opens downwards. You can use that too. The true mathematical way to describe this would be called concave up. Okay, if you guys remember from like physics and stuff like that, when you talk about like lenses, okay, concave lenses are those lenses that the ones that bend in, right? Okay, so that's the concave part right there, and the concave part is up, right? Whereas here, this concave part is down. There's actually a more official mathematical definition than that, but we're not going to worry about that right now. Okay, so concave up, concave down. Okay, that change in the orientation, right, then creates maximums and minimums. So, for example, right here, right, when we are concave up, do we have a maximum for this function? Is there a maximum here? No. Is there a minimum? Yeah. And where is it located here? -1/2, -9/4, so -2.25, which in other words is the vertex. Yeah, okay? So the minimum, right, of a parabola that's concave up, and I'm going to use those words because this is honors class, right? We're going to use the great words here. This is concave up, all right? So the vertex is the minimum. So then if we have a parabola that's concave down, like this one, our vertex becomes not the minimum, the maximum, right? And so we have a concave down parabola. We expect then to have our vertex be a maximum. And what's the minimum for this kind of graph? What would be the minimum for this graph right here? Negative infinity. There isn't one. Exactly right. There isn't one, right? Okay. So our quadratics are only ever going to have a minimum or maximum, but not both. Okay. It depends on its orientation. Okay. And we can know by looking at the function. So let me go to that here. So let's just take a look. Okay. So let's just take a look here. Oh, I said y, and let me just. Okay, there we go. Fixed it. All right. Does f have a minimum or maximum here? What would we expect? So let me let you guys think about it for a second here. Okay, so think about that. Right. This graph, right? A is positive 3, B is negative 18, C is 20. Would we expect this graph to have a minimum or a maximum? So Jordan, what do you say?
I'm saying it has a minimum.
Minimum. Okay. Max, what do you say? Minimum as well. Okay. Jordan, why do you say that?
Because it has a positive a.
Yeah, positive a value, right? That parameter that determines whether we are concave up like a cup, right, or concave down like a frown. Okay. So we are concave up here, right, which means that that vertex is going to be the minimum of our graph. Yeah, exactly right. Okay. Exactly right. So this is going to be a minimum. You don't even have to. I'm not asking you to find it right now. We're just going to identify that kind of thing. Okay. Okay. So well then. Okay. And so then, how about this function right here? This f of x. Sorry, x is very sloppy. Will this function have a minimum or a maximum?
Max.
Maximum. The graph will be concave up like a cup or concave down?
Yeah.
Concave down, right? Okay. And so therefore the vertex is going to be up here, right? Which is, again, the highest point. So maximum at the vertex. Okay. And of course, if we wanted to find the actual maximum, we don't need to graph it, right? We can go back to what we just talked about by finding the vertex using that negative b over 2a for the x-coordinate, right? And then find the matching y-coordinate by plugging that x-coordinate back in, okay? So we can actually find the vertex coordinate there that way. Right? Okay. One more for you here. Okay? So we went through graphing, talked about maximum and minimum, and now I'm going to do a word problem with you. Okay? So, any questions on the graphing or anything like that so far up to this point? Anyone, like just about the previous graphing stuff that we did? Okay? So again, these are the key kind of steps you should follow, right? Get your vertex. Use x equals negative b over 2a for the x-coordinate. Okay? Make a table. Put that vertex in the center of the table. Okay? So, right there in the center. Pick some points before, pick some points after. Okay? And then find the matching y-coordinates by plugging back in. You can also use your graphing calculator to speed things up if you want to for that table stuff, but you should be able to make this table without a graphing calculator, okay? You should be able to do that without a graphing calculator. Just a heads up, okay? And then you plot the points and connect the dots. All right, so, and hopefully I'll be able to give you some time to work on this, but let's do this first. Okay. A go-kart track has about 380 racers per week. Oops, oh, there you go. Oops, and charges $35 to each racer. Okay, estimates predict there will be 20 more racers per week for every $1 reduction in the price. Okay? Makes sense, right? You lower the price, now people be like, ooh, it's cheaper, let's go, kind of thing. All right? And somehow they were able to figure out and this is, through studying and stuff like that, you can actually do this kind of thing, okay? That if you, by each $1 you reduce it, you are going to get 20 more racers, okay? We're going to write a function, okay, for the money made, i.e. the revenue, okay, based on X reductions. Okay, good stuff. So the go-kart track has about 380 races per week, and they charge each racer $35 to race. Okay, I guess it's not like per it's not per race. It's just you just pay $35 flat fee, boom, you race. And then estimates predict that there will be 20 more races per week for every $1 reduction in price. Write a function for the money made revenue based on X reductions. Okay, so let's start out, right? Because this is like maybe intimidating. You look at this, you're like, I have no idea. Bless you. Okay. Let's start out with like the very basics here, okay? Let's forget about the reduction part. So forget about everything except that first sentence, okay? So just with that first sentence, okay, how can we figure out what the revenue is just for that first sentence? How much money do they make for that situation with no changes? What will we do? 35 times 380, right? $35 for each racer, and if they get 380 racers a week, then that's going to tell you how much money they make. 35 times 380, that's how much money they bring in from their go-kart track, right? So, 35 times 380 is equal to the revenue. No changes, though, right? But that's not what the situation is saying, okay? The situation is saying that we're going to gain 20 more racers every time we reduce the price by $1. And we're trying to write a function based on X of these reductions. Okay? So what's going to happen to the price based off of these X reductions? What's going to happen to this price? It's going to go down, right? So mathematically, we're going to represent that by what operation? Subtraction, yeah. 35 minus how much money is it going down by for each reduction? $1, right? So it's going to be 35 take away $1 per reduction times the number of reductions, right? 35 minus 1 times X. Right? Starts with $35. We're going to take away $1 per reduction. Okay? At the same time, though, this 380, what's going to happen to 380 as we reduce the price? What happens to these numbers of racers? It goes up by how much? So let me see here, 380, right? Oh boy, there we go, fixed it. All right, plus 20, and it's 20 racers per reduction. So 20 times X. Okay. Here's another question. So that's our function right there. There it is. That's going to give us the revenue, okay? Okay, I can't, my handwriting is really sloppy there. That's a revenue. R-E-V-E-N-U-E. That's that, okay? So here's the really important question, though. What number of reductions will maximize revenue? Okay. What number of reductions will maximize revenue? Well, let's multiply this out. All right, let's actually multiply this out here. So in order to multiply this out, you might have to employ, FOIL if that's what you like to say or whatever. But whenever we have two things, right, this is a binomial times a binomial, just remember that each term in here has to multiply with each term in here. So if it helps me, you can draw like yourself little arches. The 35 multiplies with these two. The minus 1x multiplies with these two. Okay? And so, yeah, I'm not going to. Okay, so we get 13,300. Okay. Let's see here. Minus 380x plus, I should know that's 700, yeah. And then minus 20x squared. Okay. Which, if we rewrite things here, I'll put it in standard form. Okay, so 320. Okay, so there is the function that describes this revenue. What kind of function is this? Is it linear? It's quadratic, right? Ax squared plus bx plus c. Okay. Does this quadratic have a maximum?
Yeah.
How do we know? What's negative?
Minus 20x.
The A, right? The A is negative. This is concave down. We're going to have a maximum. How should we find the maximum here? Finding the maximum is the same thing as finding the what of the function?
Vertex.
The vertex. Find the vertex. Okay? We're just going to find the vertex of this, which is x equals negative b over 2a. Max is at the vertex. Okay? So your b is 320, so it'll be negative 320 over 2 times a, which is negative 20. Okay? And so it's 8. Eight reductions. Okay, so in other words, they take $8 off the price. They're going to gain 160 more people, and that'll maximize the revenue. If you want to find what the actual revenue would be, then you're just going to plug in 8 there. So negative 20 times 8 squared plus 320 times 8 plus 13,300. Okay. Okay, and I get $14,580. There will be a problem like this in your homework. Okay? So you can feel free to use this to help you, kind of write it out and stuff like that. Speaking of homework, all right, so we'll stop there. All right, that's the idea, though. All right. I know I didn't give you too much time here to get started on it, but it's better than nothing, I guess. Let me do this.